This video handout concerns the basic theory of accurate mass LCMS MS, and it's part of my Accurate Mass LCMS MS basic introductory course. Understanding the LCMS MS process is much more difficult than the EIGCMS, and the EIGCMS basic course is on my website, and it might be useful if you took it first if you're actually interested in that topic. The NIS26 integrated chromatogram function has greatly simplified the identification of unknowns by LCMS/MS, thus making it possible to actually make a video such as this. And this can be done without extensive training, in my opinion. However, a basic understanding allows the user to more critically evaluate library search results, and thus the purpose of this basic introductory course. Most figures were created with ChatGPT, but I had to put a lot of effort in creating proper prompts to get them to display properly. If you don't understand my particular description or understanding of LCMS/MS, you might take a look at the two excellent videos that I have on my website as resources, the first and second shown below. I will be breaking down the talk into these following 5 topics. I have them in the block diagram shown below, into the separation, because we'll always be looking at mixtures generally by LCMS, the electrospray ionization, the precursor analysis in the first part of the mass spec analysis to get the molecular weight information for the compound, and then the product ion analysis to get additional substructural information to use for searching, and then you have to detect it all using the accurate mass detector in both the first phase, the MS1, and the MS2. And all these slides will contain a lot of information. And I put them in mainly as resources. I'm not going to step through every one in detail, but I put them here as a resource for future reference for you. HPLC is essentially the same separation principle as paper chromatography that you might have done in middle school or grammar school. You put something on a stationary phase, in this case filter paper, and you put a drop of ink, and by running a solvent the top of the phase, you'll separate the different components of the ink into the colors shown below. The same thing happens with HPLC. You have a solvent, you have a pump in this case to push the solvent through a column. You inject the sample on the injector onto the head of the column. And then you have a stationary phase that interacts with your compound, and then the detector responds to things as they elute from the column. And the data system records the signal versus time. In this case, on the detector, it will not be a UV visible detector, but instead we'll have a mass spectrometer, and the compounds will elute for the column, so you'll get the separation, with A being least retained and D the most retained. Electrospray mass spectrometry requires the presence of acids or salts for ionization, and have some acceptable ones below and ones that are not acceptable. In general, formic acid in both the aqueous and the organic phase, because it's usually two-phase solvents, the water to get things off initially, moving toward higher organic to elute things that are more heavily retained at the top end. So use volatile salts, avoid non-volatile additives, and rinse the LC when switching between incompatible additives if you're using the system for other things besides mass spectrometry. Here are some solvents that are used for reverse phase LC-ESI, electrospray ionization mass spec. The normal ones, you start out with water with formic acid, as we said, and the other one it likes to be paired with is acetonitrile. But there are others that are used at time if it's harder to remove things from the column to get them elute from the column, then you might have to pick a stronger solvent. But there are other ones over here that you probably should avoid in most cases and use with caution in others. So again, the best practices, as we show at the bottom, acetonitrile and water are the most widely used mobile phases. And the key takeaway, use volatile, MS-compatible solvents for the best ESI performance and to keep your source clean. Here's some, if you want to develop an LC-MS/MS method, here's a basic and some practical tips on how to do that. Some typical reverse phase gradient examples. You start out at high water, and then you push it to higher organic to get things that are retained, more lipophilic, or ones that stick to the column. You have to go to higher organic. But again, you have to pick systems that go along with the mass spec. the mobile phases additives, it's best to use formic acid. You can use ammonium acetate, but most of the additives or most of the spectra in the library were obtained with formic acid. So it's usually better if you can stick with that as far as trying to get identifications. And so the solvent A would be one at the top, 0.1% formic acid with acetonitrile with 0.1% formic acid. Oh, there are other ones you can use when you need to, and you have to be worried about the flow rate. And again, like we said, the additives affect what you see in the mass spectrometry data that you search by the library search. So you have some general takeaways here for general unknown ID and NIST library searching. Start with A, water plus formic acid, B, acetonitrile with 0.1% formic acid, and add ammonium buffers on if they improve chromatography or ionization for your specific analysis. Phase collapse used to be a problem on columns, but going to 100% water, not as much now for newer type columns. And at the bottom, again, some best practices checklist and a quick reference summary for the things that you might want to consider in developing a method. But if you're just looking at data, you don't need to do this. But usually, as you learn how to interpret data, you'll want to develop your own methods. So I put this in as a resource. Both positive and negative ions can be sampled into the mass spec. But somehow we have to turn liquids into ions, and they do this by using a nebulizing gas to make an aerosol, and that's heated. But they also use a high voltage with respect to the front of the instrument of about 2 to 5,000 volts, and that helps make the aerosol. Between that, and we're also at atmospheric pressure, so collisions with gas molecules, nitrogen usually in here, will cause the droplets to be formed and just break up. And then after they get to an ion, they go into the mass spectrometer. I'm looking at positive ion here. You have to change the polarities to do negative ion. But it goes through a capillary because we're at atmospheric pressure here. We're at very high vacuum as you go to the mass spec. So if you look at it in the bottom, I'll state it again. When we start, we have, of course, a liquid, and we have equal number of positive and negative ions overall in the solution. So if you look at the solvent evaporation, as they start to evaporate, some droplets start to get more excess positive than negative, etc. And sooner or later, you get the Rayleigh limits reached where the electrostatic repulsion overcomes the surface tension that you had to do with the solvent. And then after that, as it droplet breaks into many smaller charged droplets, the charge gets higher and higher, and they tend to explode. And sooner or later, further evaporation as you're going through the nitrogen and the atmospheric pressure, you get positive ions, and then the ions are drawn into the mass spectrometer where they're analyzed. Of course, we can only see ions. We do not see neutrals. Neutrals are not detected in the mass spec. Here's a total ion chromatogram, a TIC, of MS1. So this is what you would see in the NIST software. You'll see an ion chromatogram. It sums all the ions seen by the mass spectrometer during the analysis. So it essentially stacks all the ions it sees on top of each other to give you this total ion current over here. And it shows you versus time what they are. And each is essentially the molecular weight of the compound for singly charged compounds. And most of the ones, all of the ones that I will discuss in this course are smaller molecules, and they tend not to support more than one charge. But if you get bigger molecules, you can get doubly charged compounds, and then their mass to charge will be, the mass observed will be half because the charge is 2. But in our case, it is almost all, essentially all will be a charge equal 1. So what you see in MS1 will be the molecular weight of the compound. Beware, the response factors for compounds can vary widely. They're not the same for the amount of material you put in. It just depends on how they like to analyze. And again, usually in positive ion mode, we'll see M+8 ions. Here is the MS1 spectrum of compound that elutes at retention time 5.21 minutes. As we said, this will be a low energy spectrum, so there won't be hardly any fragmentation. So usually the charge is equal to 1, as we said, for all the compounds that we will talk about in this course. So the mass to charge equal the molecular weight of the compound plus the weight of a hydrogen. Somewhat like a microbalance for measuring weight of an ion. The mass accuracy is often much better than plus or minus 5 parts per million. And note the other information presence, the isotope ratios for C13. So we have this is all C12 at 244.2058. But if you go over it's approximately one mass unit, that'll be for the molecule that contains, or the group of molecules that contains C13. And this is another group that contain molecules that have two C13. So the probability falls off pretty quickly. So this is pretty powerful. It shows the isotope ratios between the elements, which is very specific, and the accurate mass. So that really narrows down the possibilities for candidates, even in the MS1 before you've actually done the MS2 part of the experiment. So if you look at it again, this is the phencyclidine. It has a precursor at 244.206. And you can see the isotopes that contribute to these isotope ratios. We have carbon-13 is about 1%. So for every 17, the probability that the molecules would have carbon-13, the M plus 1 would be about at 17%, probably the number of carbons times the percentage. Other elements have isotopes also, but nitrogen, oxygen, not so much. Silicon starts to have significant 28 and 29 and 30. And sulfur has 32, 33, and 34 of these ratios. But chlorine will be very distinctive because the ratio of 35 to 37 chlorines is almost 75 to 25. So you'll notice that very distinctly. And we'll show that in another molecule in another example on the next slide. Of course, the bromine. But the software in the NIST 26 has something it calls its XIC analyzer. And what it does, it generates the isotope ratio theoretical for what it thinks it will be and then compares it. This is actually two different colors here, but you can see they're almost identically matched. So the theoretical versus the actual is dead on. So very good results. And also on top of that, the mass accuracy for this ion is within 1.6 parts per million of the theoretical, and even less than 2 and 3 even for the double C13. So you have a lot of information that points this could be a very good candidate for this compound. So we go into the MS1 spectrum of compound at retention time 8.31, and this one does have chlorine in it. You'll look here, you'll see the presence of the chlorine over 2, so you have that very definitive pattern for it. You'll have a little bit of the sodium ion addict. We didn't add sodium on purpose, but it's in the background of the mass spec in the solvent systems in the column, so you'll often get sodium addicts. And if we look at the XIC analyzer again for this, you'll see almost perfect matches on the ratios again, between the two colors. They're identical. And the mass accuracy is 0.8 for the all C12. And for the C13, you can see it also within 0.3, 1.6 for the one that contains 1 chlorine 37. So very good fat, very, very good fit. So that gives you confidence that this is very consistent for this molecule. So that would be a very good candidate. So I just wanted to show you some other ratios for M plus 2 elements. These are all 2 apart here. You don't really see a mass scale, but this is our chlorine pattern for 1 that we saw in the previous molecule. But you can tell that 2, 3, the bromine 2, mixed chlorines, they're all very definitive. And I'm not saying you have to determine or remember how to do this because the data system's very good at matching isotope patterns with the computer, but it takes advantage of these very specific patterns, and on top of that, the mass accuracy. So I want to state it one more time. Why does mass accuracy and isotopic fidelity matter in MS1? In MS1, accurate mass and correct isotope pattern together confirm the elemental composition and increase confidence in the compound identification. So if you have very low part per million error and in the XIC analyzer part of the program shows a very good match to the theoretical versus the actual isotopic pattern that gives you very high confidence, while in this case it's not that far off in parts per million, but the isotopic envelope, the isotopic fidelity is very poor, so low confidence, and that one would be eliminated, so you get fewer false matches. So here is the MS2 spectrum of the compound at retention time 5.21. So as the instrument is going along looking at the MS1 ions, if it detects a major ion precursor in MS1, such as here 285.0785, it'll automatically select that ion and put it into the collision cell to yield an MS2 spectrum at higher energy to yield fragments. So then the NIST-26 uses the MS1 mass accuracy and isotopic fidelity plus the MS2 data to search the library and identify the compounds. Though there's just so much information in the MS2 spectrum, you can see it still has some of the precursor here that wasn't broken into pieces, but it gives ions that are at 4 significant figures that are probably a little bit less accurate than in MS1, but not significantly. So if it's outside a certain window here specified by the program, it'll also penalize the result and will not give it as a possibility. So between all of this information, it's gives you a very good idea of what the compound's identification might be. Also, we have a program called MS Interpreter within NIST that looks at any ion and proposes a substructure. So if you pick this ion at 228, which is this small ion here, is off by only zero point 0.7 parts per million. So it knows that this is a likely structure for the unknown. And you can look at all the ions like this and get proposed structures. I'm not saying that you have to understand the fragmentation now, but it's a good tool as you're looking at data to learn how things fragment in MS2. So it's a good teaching tool. This is my concept about how the NIST-26 chromatogram window performs identifications. The documentation doesn't say exactly, so I made some assumptions here, but from what I can tell, if you look up here in box 1, the precursor and the master charge within a user part per million window, which is usually 20 in my analysis, should have the same peak shape, should have the very similar isotope profile, and the charge state should be 1. And then when it does that, it'll pass these 9 spectra that it thinks are all representative of one component that it'll try to identify by library searching, and it puts it in XIC bin number 472 here. If you look up at the top here, there were 9 spectra, as I said, and there are 559 XI bins in this analysis of this file. So there's a lot of things that it grouped together, but this is the one I wanted to show you. And if you turn off the best hit within the display, you can see all 9 spectra and what all of their scores were. And you can see that there's some very low. So if you tried to average these, it would probably take away from the search quality. And so that's really why they tend to just take the best hit. And also, there's also 2 scoring, the dot product. The dot product over here on the right measures spectral similarity of fragment ion intensities. And SCORE is the preferred NIST ranking statistic because it includes additional spectral quality considerations applied on top of the dot product. So when you turn best hits off, this is what will go into the report. Diazepam, it'll have the retention time, it'll show what library it came from, and so that'll be the final thing in the table. And like I said, there were 9 spectra for this compound and that were diazepam that it thought was related in bin 472. But overall, there were 559 things that it put in bins and did library searches to find the best hit for those different bins. So what's other reasons for the best hit reporting in NIST-26 for library searches? Well, MS2 spectra vary from instrument to instrument, and the library must contain many different spectra using different collision energies to reflect this. In the case of diazepam, there's 48 in the reference spectra library for it in a variety of collision energies. By selecting the best hit approach for a spectrum in an XIC bin, NIST found that that gave the most reliable search results. And you can see the results over here. I've got best hits turned on, so I only see the final results. So you can see the diazepam reported with the unknown on top and the best hit on the bottom. And we'll go through this table in detail when we look at the actual software. So talked about Agilent, in this case, doing an automated MSMS such that every time it detected MS1 ion that thought was significant, it would trigger an MS2 spectrum and at higher energy to get fragment ions. And so this is very good when you don't know what's in the sample, but you do lose some sensitivity because when it's sampling one ion, it might not sample the ion that you want. That's a more major ion. So sometimes instead of doing this automated uh, data-dependent acquisition, they do targeted MSMS, and the NIST software will process both. In this case, you run an MS1 and you decide all the ions that you're interested in, that you think are the major components, and then you set up a target list with retention times and masses that you want to monitor for the precursor ion, and then you get the MS2 spectra. And this gives you more samplings across the peak, so you tend to get better data. So a lot of times if you're trying to get the highest quality MS2 spectra, this would be the way. But of course, this takes a lot more time if you're having to do this on every sample. So the automated actually works reasonably well, or very well actually. So usually you run that, but sometimes you'll want to run a targeted run. Different vendors call it different things, and that gets a little confusing to me. So I've made a table here of the common names for automated for the different manufacturers versus targeted for the different manufacturers. I just wanted to compare the QTOF to the Orbitrap. Those are two of the most common instruments used for accurate mass LC-MS-MS. You'll see up front will be very similar in many cases, but on the time of flight, you have a quadrupole here that selects the mass that you want to throw into the collision cell. If the collision cell is kept at low energy, you get the MS1 spectrum from the ion mirror, the time of flight part of it. But whenever the data system decides it wants to sample something, it takes that ion and throws it through this collision cell at higher energy, and it's got some argon gas in there at lower pressures, and that causes the compound to break up and give you the fragment ions. The Orbitrap's much different. It has some for precursor ion selection up front, but it also has the C-trap where it can send things down to get the accurate mass for the MS1 and also decide if it wants to fragment an ion by sending it into the collision cell and then back into the C-trap, back to the mass analyzer to finally get the MS2 spectrum. And the Orbitrap is a very sensitive instrument, so it does a really good job of doing MS-MS analyses, but we can get very good data from a QTOF also. Accurate mass LCMS is very much more complex and expensive than nominal mass EI-GCMS. In GCMS, you use a 70 electron volt beam, and you get very reproducible spectra in the gas phase for the compounds. So you really only need one spectrum in your library to get a good match. NIST does have some replicates, but in general, most of the replicates are actually pretty good for searching also. There's not very much variation between even the main library spectrum and the replicate. And EI only uses positive ion mode, and it's done in a vacuum, so the molecules don't usually interact with themselves. In electrospray, you have variable collision energies that are compound dependent, so it's just hard to reproduce all of these variables within the instrument. So you'll need many different spectra, such as the case of the diazepam. It had 48 different spectra in there in the library, and you'll have to have all of these spectra to get the analysis of one compound. The other nice thing about electrospray is you can do both positive and negative ion modes, and that can be very useful. And the solution analytes occur at atmospheric pressure, and they form droplets. That means that interferences in this droplet can suppress the ionization of the ions because it's not in the gas phase. It has to do with the evaporation. So compounds that are present in with the compound you want, maybe as a background, can have matrix ionizations effects and give much different spectra depending on the matrix. The other thing about EI, the EI, if you run an EI chromatogram, you scan the full spectrum, the responses are somewhat related to the concentration. The electrospray, you can't really count on that. The responses are so much different depending on how effective this evaporation is for the class of compounds that you have. So it's just very hard without getting a standard to quantitate an electrospray. You might use a UV detector and have similar things in the sample, and you could use the UV detector that was in series with the electrospray. But by itself, it's difficult to get an idea of even relative concentration as an approximation. So, that being said, what's so important about LCMS/MS? Well, it's the type of compounds that could be ionized. So if you look at this chemical space of the whole compounds that are present in the world, let's say, it's kind of hard to say what the size of the circles should be, but in general, the number of compounds for EIGCMS are much smaller than those that can be analyzed by LCMS. They have to be stable and volatile. You can make them stable and more volatile by making derivatives, and NIST goes to a lot of effort to add derivatives of all the compounds that they buy to the library. So if you make a derivative, you'll find it when you do the search. But to do these other compounds, this enormous diversity of compounds, you have to have LCMS/MS because they're just too large and unstable to actually make it through a GC column. So that's what makes the power of LCMS/MS. Of course, the complexity goes along with that ability. So I hope this video has helped you understand the basics of LCMS/MS and hopefully will help you as we go into looking at the software and evaluating the results, since you understand a little bit more about the limitations of the analysis. Good day.